Yes, I
Now
do.
there is none.
Oh, I'm so sorry. I'm so sorry about that.
Now
Yeah.
there is none.
Yes.
So there is a little like piece of paper with instructions.
Okay.
But basically,
Yes.
so this is for the projector. So
Yes.
on off.
I can do
It says
that.
standby, but it's off.
I can handle it. Okay.
Okay, that's for the
Yes.
camera controls. Zoom in on,
Oh,
but that's
just
like.
leave it alone. Okay.
And as for the input, there are a few buttons here.
Okay.
You need the one with HDMI.
Got it.
Yeah.
Got it.
Some other buttons might be pressed, but you need the one with HDMI to make this.
Okay. Perfect.
And then it's supposed to like.
Okay. Thank you very much. Thank you very much. And before I forget, there is a stick for pointing, and, and also self-defense in case you have to.
In case the audience gets particularly upset about the things I'm saying. Or even bigger stick. That's
I mean, like, whichever you prefer.
whichever you prefer. Either, I guess, yeah, I'll just stick with this one. It looks a little bit longer.
Yeah. Yeah, but somehow something there was some other.
Okay, so right, let's start. So we are very much delighted to have Professor Sharpe today from Virginia Tech. So Eric graduated in Princeton, then he did postdocs in Duke University, Illinois, Urbana, and Utah University, and since 2007, he's a faculty member at Virginia Tech, and he's going to tell about some exciting things about gauge theory multiverse.
All right, well, thank you all for having me. I think this is only the second time I've ever been here. The last time was over a decade ago. I'm going to be talking about, well, as you can know from the title, generalized symmetries and some of the more exotic implications of generalized symmetries in quantum field theories. And this is, as you can see from this list of papers, a topic I've been thinking about way too much for far too long for good measure. Also, feel free, let me say at the beginning, feel free to ask lots of questions. If memory serves for my last visit, that's not a problem, but please do feel free to, please do feel free to jump in. It's all good. All right, so I'm going to begin today with a quick review of something we all know about quantum field theory, because this talk is going, at least part of this talk is going to revolve around it. Namely, the fact that path integrals sum over all instantons. Restrictions to subsets of instantons aren't allowed, or at least they're not supposed to be allowed. So this is an old argument that was due to Weinberg back in the 70s. Let me give the cartoon version of Weinberg's old argument. So let's begin by demanding that the total instanton number always vanish, just hypothetically. Let's start with a field configuration with no net instantons. Weinberg's argument was that given such a field configuration, we could always arrange for it to sort of look like an instanton and an anti-instanton that were close together, and then separate them out to some long distance. There we go. And then once they get separated far apart from one another, we have a region with instantons and another region over here, which also has instantons. And if we believe that cluster decomposition works, then whatever we thought about our quantum field theory, we have to consider configurations with instantons. So if physics is local, if cluster decomposition holds, then in these widely separated theories and these widely separated regions, the theory has instantons. So even if we start with no net instantons, cluster decomposition implies we get instantons. So for this reason, Weinberg taught us that all local quantum field theories must sum over all instantons. Otherwise, there's some sort of failure of locality that must be present in the theory. Now, one thing we've learned by generalized symmetries is that at least sometimes this rule can be broken. It is possible there exist local quantum field theories that only sum over a subset of the instantons in the theory. And the answer is one aspect of a phenomenon called decomposition, which I'm hoping to outline today. So before getting into details, what is decomposition? Well, briefly, decomposition is a statement that a d-dimensional quantum field theory global D-1 form symmetry. I'll explain what a higher form symmetry is in a few minutes. Bear with me. I'm just trying to set up the basics of the moment. This thing is equivalent to a superposition or disjoint union of other local quantum field theories, which in this context have come to be known as universes. So if schematically this picture is our local quantum field theory, then sometimes what we thought was just one local quantum field theory is really a superposition of several different local quantum field theories. And then sometimes instanton restriction can result when contributions from several different universes cancel one another out. So my goal today is to explain this as well as some related phenomena that can arise in decomposition.
So here you separate space.
Or it's quantum field theories that don't talk to one another otherwise. So I mean, whether you talk about them as being on one space-time or separate space-times, if they don't actually communicate at all, then it's sort of a moot point. If you
have different space-time, it's in the same space-time, but separated by gravitation.
Oh, these theories aren't going to be coupled to gravity. I'm not going to include any gravitational coupling. If you toss in gravity, I don't want to think about gravity in today's talk.
So
Exactly. This is just quantum field theory, not coupled to gravity at all. So here's an outline of what I want to talk about today. First, let me begin by reviewing ordinary and generalized symmetries. And then what I want to do over the span of the talk is talk about some key examples that I think will be of interest to this crowd. I'm going to begin by talking about four-dimensional Yang-Mills with instanton restriction, and a way to describe this as a local quantum field theory due to Mehta-Denzel and Yuya Tanizaki, and how this is equivalent to a superposition. And then I'll talk about some other examples. Prototypically, two-dimensional SU2 theories with center invariant matter, or more generally, two-dimensional G-gauge theories with center invariant matter, and how they're equivalent to a superposition of other theories. I'll talk about two-dimensional pure gauge theories, which is sort of an extreme version of this. And I'll talk about two-dimensional real gauge theories. And to be clear, there are lots and lots of examples, but I figure for this audience, people are primarily going to be interested in gauge theories. But if you're really curious, stick around afterwards and I can tell you everything you never wanted to know about orbifolds and more mathematical things. But this is going to be the heart of the talk. All right, let me turn to symmetries. Let me begin with a quick review of ordinary symmetries and describe how generalized symmetries fit into this framework. So classically, as everyone here knows, recall that a group defines a symmetry of a theory if the action is invariant under the action of that group. That leads to Noether's theorem and conserved currents. There's a quantum mechanics version of this. Given a group, we can represent elements of the group by unitary operators, such that the unitary operators respect the group structure. The product of the unitary operators corresponding to group elements is the unitary operator corresponding to the product of the group elements. And then we can also represent that infinitesimally. We say it's a symmetry if it commutes with a Hamiltonian in the sense that the Hamiltonian is invariant to the conjugation, or equivalently that the generators commute with the Hamiltonian, either way. Just as a simple example, and I think everyone here will be aware of this, but just to get everyone pointed in the right direction, so to speak, let's talk about gauge transformations in electromagnetism. So here, physically, if A is a gauge field of electromagnetism, then as everyone here knows, we identify A with A plus D alpha for alpha any function. And we can make that identification because both A and A plus D alpha define the same electric and magnetic fields. So this alpha describes an infinitesimal action of the group U1. And since we're identifying fields related by that action, we say we've gauged symmetry. Now, how can this be generalized? How can we talk about, what can we do to, get higher group structures or different, what do people mean when they talk about generalized symmetries? Well, one way to generalize these symmetries is to weaken some of the group axioms. So for example, associativity. And don't worry if this looks a little mathematical. Most of this talk is going to be about gauge theories, but I want to try to, root this in some more nearly concrete description of what a generalized symmetry is. So ordinarily in a group, we require that the group product is associative. G1 times the product of G2, G3 is the same thing as G1, G2 times G3, that it doesn't matter where we put the parentheses, the result is the same. So it's one thing we can do to get a generalized notion of a symmetry is to weaken that. In a what's sometimes called a higher group, we can instead merely require that this and this be isomorphic to one another, where the isomorphisms themselves have to satisfy some higher tower of constraints. And don't worry, I'm not going to be running in the direction that that would imply. But again, I just wanted to give people some concrete idea of what people mean when they talk about generalized symmetries or higher form symmetries. Yeah, I mean, technically this would be part of the two group. And then there's extra structure. I mean, really, you'd want to just not weaken not only associativity, but also how the identity operator acts. So G times G inverse will be isomorphic to the identity, but not necessarily the same as the identity. You can weaken all of the group axioms and then impose, you need to impose requirements like this to tie them all together, but it's disgusting and yeah.
I'm sorry, just as a distraction.
No, it's all good.
But when I have run into higher groups in some part of the physics literature, they appear when you have intertwining normal symmetries and higher form symmetries. Like,
oh yes,
that's obvious in this presentation what this has to do with that.
So that also can arise. For example, we could take a simple example that we'll be encountering at some level later will be we can build a group out of we can build a higher group out of products of bundles. So start with an ordinary, say, a Lie group G. We can talk about the set of G bundles, and we can put what's basically a higher group structure on the set of G bundles. At least for G abelian, we can multiply G bundles together. So there's some notion of a product. A product of G bundles will be associative in this sense. We have to be a little bit careful about when building those products, but you can do something like that. And then as part of that, you can also build, for example, extensions of ordinary groups by higher groups. There's a bunch of games you can play. So this is just sort of the most basic.
Thank you.
So as a concrete example, let me talk a bit about B fields. So the B field is a two-form tensor potential with a gauge invariance. B goes to B plus D lambda, where lambda is a U1 gauge field. So in this example, the gauge transformation itself admits gauge transformations. A gauge transformation by lambda is equivalent to a gauge transformation by lambda plus D alpha. So as a result, gauge transformations can only really be isomorphic to one another. So something like associativity of gauge transformations is only going to hold up to, well, a second level of gauge transformations. Associativity only holds up to isomorphisms. So, as I'm sure everyone here knows, fields of this sort are very common in string theory. Now, in this context, one can think about how to try to generalize ideas like Noether's theorem. Let's go back and remind ourselves how Noether's theorem works. Let's go back to ordinary symmetries. Consider an ordinary global symmetry. Under an infinitesimal symmetry transformation parameterized by some alpha, we can say that the action maps to the action plus d alpha wedge j. Or usually we describe this as in terms of, well, really a Hodge dual of this, but we could just write this in terms of s goes to s plus d alpha wedge j, where j is some d minus 1 form dual of what we would usually call the Noether current, which obeys, importantly for us, dj is equal to 0. This is a statement of the conservation law following from Noether's theorem. So given such a j, formally we can associate some operator that looks like the exponential of the integral of j, supported along some submanifold of dimension d minus 1. Because of this conservation law, because j is declosed, we can deform this manifold and get, without changing this operator. So this is, as a result, this is what we call a topological operator. So this turns out to be one more efficient way, or one commonly used way, to think about generalized symmetries in terms of operators. Now, so far, I've only talked about operators for ordinary symmetries, but there's a way we can soup this up to talk about more general cases. So consider a symmetry parameterized not by a zero form, not by a function, but by some p form alpha. then one can imagine that under a symmetry transformation, the action might map to itself plus the integral of d alpha wedge j. Same expression as before, it's just that the interpretation of these as forms has changed. Alpha is now a p form, j is now a d minus p minus 1 form, but still closed under d, still obeying this conservation law. Given such a j, obeying this conservation law, we can associate an operator that's simply the exponential of the integral of j over some suitable submanifold. And because of the conservation law, this operator is still invariant under deformations of that manifold. So this is one way people are thinking of nowadays of higher form symmetries, in this case of p-form symmetries. In this language, ordinary symmetries are referred to as zero form symmetries. So when I talk about D form symmetries or D minus 1 form symmetries or minus 1 form symmetries or what have you, this is sort of a good picture to have in mind for what's meant by that kind of language. Now, let me circle back to the statement of decomposition. So the claim is that a quantum field theory in D dimensions with a global D minus 1 form symmetry is equivalent to some superposition of other quantum field theories, which often results in instanton decomposition. Now, we've seen this in examples since 2006, but I want to begin with a more recent example that I think cleanly illustrates what's going on and may be more interesting to this group, namely an example involving instanton restriction in 4-dimensional Yang-Mills. This is a result due to Metaranzo and Yuya Tanizaki from just a few years ago. So their argument goes like this. Let's start with ordinary 4-dimensional Yang-Mills theory, for which I've written the action right there. Now let's modify this in the following way. Let's add a scalar field of periodicity 2 pi and a 3-form potential, the C3 up here, together with some interaction terms. These interaction terms right here. Well, locally, this H is dC3. So that C3 is, this H is the curvature of that C, and then this K is some integer. Let's think about the implications of those fields and so forth. Well, first, if we look at the equations of motion for B, B is basically acting like a Lagrange multiplier. So it's going to force trace of F(y)F to be some integer multiple of H. The integral of H is going to be an integer. What this is implying is that the instanton number, the integral of this, will be K times an integer. So as a result of adding in these terms, we should get a theory in which the instanton number is divisible by K. So that, off the bat, is instanton restriction, and instanton restriction in a local quantum field theory. So this would appear to, well, not just appear to, this violates at least the spirit of Weinberg's rule back at the beginning. This is an example of a local quantum field theory, which violates instanton restriction, or which has an instanton restriction and so violates Weinberg's rule. Now, as discussed earlier, restrictions on instantons violate cluster decomposition. But note, there is also a global 3-form symmetry in this theory. Namely, I can shift C3 by some other 3-form that is D-closed. So when I say a global 3-form symmetry, what global in this context means is that I'm shifting by a 3-form that's closed. This right here is the implication of having a global 3-form symmetry as opposed to a local one. So since lambda is D-closed, C goes to C plus lambda leaves this H invariant. So if H is invariant, that's a symmetry of the action. Now from the yoga I've expressed earlier, this then is a 4-dimensional theory with a global 3-form symmetry. So I expect some sort of, I expect this to be equivalent to some sort of superposition of theories. So how can we see that? All right. Well, if we look at the equations of motion for C, the equation of motion for C was buried inside here. So if we just flip the exterior derivative around, the equations of motion for C imply that dB is equal to 0, modulo being careful about constants and the fact that B is periodic. In fact, if we're a little bit more careful, we can argue that B is not just constant, it has to be one of a finite number of constants in order for this action to be well defined. So B is going to take on one of k possible values. Now, if we integrate out B and C, what happens? Well, B can only take on finitely many values, so the path integral has to sum over those values. And the result on a connected space-time looks like the following. The partition function of this whole theory formally is a sum over values of B. That's what the sum is doing of the path integral over gauge fields and Faddeev-Popov ghosts and so forth that I've suppressed. Here's the original Yang-Mills action, and then here's what remains of those terms that were added. We still have this trace f wedge f. The value of B is now absorbed into this factor here, and the C term is dropped out when we integrated out C. So if we look at this, again, this is all that this descends from these extra terms that we added, but this is just a theta angle term. So here we've got the usual Yang-Mills action. We've added a theta angle term. So each of these pieces we're summing over is just ordinary Yang-Mills together with some theta angle that's basically a kth root of unity. So this is the partition function of a decomposition, a superposition of k different quantum field theories called universes, each an ordinary Yang-Mills, each separately summing over all instantons, but each with a shifted theta angle. So just to recap, we started with a four-dimensional Yang-Mills theory, a local four-dimensional Yang-Mills theory with a restriction on instantons, whose construction involved a global three-form symmetry, and we've discovered what looks like a decomposition. We've discovered a partition function that looks like a sum of partition functions of ordinary theories. Well, if I express this graphically, I can describe it something like this. So on this side, schematically, I have the Tanizaki-Unzold theory, their local quantum field theory, which is Yang-Mills with a restriction on instantons. On this side, I have the sum of a whole bunch of ordinary Yang-Mills theories, each with different theta angles. And what I've attempted to illustrate here is that instantons whose instanton number isn't divisible by k come with different phases, such that when you sum them up, they cancel out. So if the instanton number is 0, fine, that gets multiplied by a phase of 1 in all these theories. If it's k or a multiple of k, fine, nothing happens there. But for all other instanton numbers, these will all get multiplied by a phase which is different between these different universes. So just like when you sum over roots of unity and get 0, you get a cancellation. And so on this side, got a sum of ordinary Yang-Mills theories for which the instantons cancel out, giving you this theory with a restriction on instantons on the far side. So going back to Weinberg, as I said at the beginning, Weinberg taught us that all local quantum field theories have to sum over all instantons so as to preserve cluster decomposition. But what I've implicitly argued is that there's a loophole in Weinberg's argument. Disjoint unions also violate cluster decomposition, but for trivial reasons, and they're straightforward to deal with. There's no real, essential difficulty in locality. It's just that it's a disjoint union of quantum field theories. So as a result, so long as a theory with restriction on instantons is also a disjoint union of theories, so long as each of those separate theories is a well-behaved quantum field theory, then everything should be okay. There's not really a problem. And that's the spirit in which decomposition can give rise to a restriction on instantons without fundamentally doing anything too terrible. Yeah, go for it.
So imagine for the sake of argument that we did all this, but we actually broke the three-form symmetry a little bit.
Mm-hmm.
There's some brains or something that the C field coupled to, but they're very heavy.
Mm-hmm.
Can I think of that as so like in the theory where we have the exact symmetry? It's like we've removed essentially a bunch of instances. But when we couple all these different universes together, because they're these tiny brains, is it equivalent to saying that we've given some extra core energy to the instantons and the core action, roughly speaking, so that many instantons have much higher action than others? And so they would therefore make a smaller contribution to the action. Is that a visual picture?
I think so. I mean, there's another example that's that comes up, which is I'm not going to have the time to talk about today, but it's sort of in that spirit. So there's one of the applications of decomposition that I'm fond of, sort of my favorite application, is to describing geometries in case linear sigma models. This will take about 3 minutes, so if you all will bear with me while I try to sort of hand wave my way through a different example. So this is an example in which decomposition gets applied in a Born-Oppenheimer type setting. So you have what looks like at low energy some parameter space over which mostly you have a decomposition, but then there's some subloci along which the decomposition is broken because of the one form, well, it's a two-dimensional example I'm thinking of, and the one form symmetry stops being true at these subloci. So in some Born-Oppenheimer sense, mostly you can apply decomposition, but it breaks down at a few places. And then what we get is essentially a branched cover of the parameter space in which we have a decomposition generically, and then the different sheets of the decomposition join together at those places where the one form symmetry is broken. So ordinarily I would describe that a little bit differently from, I wouldn't quite, I'd have to think about it. I don't know that I use quite the same language, but I think
the thing that's behind my question is whether one can try to use any of this for strong CP purposes. Because what this is doing is it's messing with the instantons. This is some way of, so you see, normally we think that it's not like UCD just have the actions they have, that's it, there's no further discussion. But by playing this game, it naively seems like you can construct theories in which instantons have a little extra core action, raise them, right? And that naively would then suppress vacuum energies, the vacuum energy dependence. So it makes me wonder whether there's some practical juice that can be squeezed out of this strong CP.
I know that's one of thinking. Midhat was very curious about whether CP could be addressed with this, and he finally concluded that it wasn't directly relevant, but I don't know, what he could say. There's one, but but it's a fun question. So, for example, we talked about real gauge theories a few minutes ago, and there's an old paper of Banks and Seiberg, maybe Bankstein and Seiberg, where it was written back in the early 80s, but they did something that's closely related to what I'll be describing later. And the motivation for the paper was exactly to understand the CP problem.
Yes.
But yeah. So they ended up describing it just as some toy model, but yeah, let's yeah.
The initial theory on US1 form is it's not propagating user freedom.
That's right.
And
That's right.
So my question is, when you try to make your instanton divisible by k, I think somehow this plays a role. You're not, you're absolutely allowed to add the dynamical, which is D-1 form, division form. You can do that, and then in that way, also by introducing the Weinberg modifier, which is B, and you can just instantly divide. So does that play a role? Does that affect the D-1 form? It's not appropriate to use the form.
That's right. It's not giving rise to any propagating degrees of freedom. That was also the case in the Yuya and the Tanizaki Anzo example from a couple of minutes ago. The extra fields they add aren't actually propagating. It's a point they make in their paper, or don't contribute any new degrees of freedom. It's a point they make in their paper, which I just suppressed. More generally, that's also true, but there can also be weird, sort of exotic mixed anomalies, which is part of the reason why you get different choices of why you get variable theta angles as you walk through this. So let's chat later. I think maybe that's the best answer. I'm going to probably revisit various permutations of this over the course of this talk as I wander through other variations. All right. So let me quickly page through. Right, let me also take a minute to try to distinguish these disjoint unions or superpositions from some other notions, like the notion of a tensor product. A theory of two free scalars is a tensor product of two copies of the theory of one free scalar, But one thing to emphasize is that this is different from a superposition or disjoint union. I mean, the language of disjoint unions and tensor products sounds kind of similar. So I wanted to emphasize that these really are different notions. When I talk about disjoint unions or superpositions, I really mean something different from a tensor product. For example, that there will be multiple identity operators in a disjoint union, but not in a tensor product. Let me be a little bit more precise about what I mean by a superposition or disjoint union. One thing a superposition or disjoint union has is in principle projection operators. Depending upon the theory, they might not always be easy to find, but in principle, if you're claiming that the theory is equivalent to a disjoint union, the theory should contain some topological operators that act as projectors. They're orthogonal projectors in this case. If I take one of these projectors and multiply it into itself, I should get the projector back again. They should be complete in the sense that if I sum over all the projectors, I should get the identity, and they should commute with everything. So since the operators are simultaneously diagonalizable, since they, for example, commute with one another, the state space of the theory breaks up into a sum of spaces, essentially eigenspaces for each of these projection operators. And then if you think about correlation functions in a theory with such a set of projections, here's a random correlation function. Here I'm inserting the identity, just a sum over projectors. Since the projectors square themselves, I can take that projector and sort of multiply it out and move it to multiply each of these other operators and rewrite this correlation function ultimately as a sum over projectors of a correlation function of O twiddles, where each of these O twiddles is just an operator in the original theory multiplied by a projector. In effect, a sum over universes of a correlation function in each universe. Well, that's a little formal, which sort of illustrates the yoga behind how these superpositions are going to work. And then a result I've already used, partition functions. If I think of a partition function formally as some sum over all states of some exponential of minus beta times Hamiltonian, then if the state space breaks up like this, I can write the sum over all states as a sum over universes and a sum over states in that universe, so as to write this partition function as a sum of partition functions for each of the individual theories. This was already the output of the Tanizaki-Unzel construction, that expression for the partition function of that decomposing theory as a sum of partition functions of constituent theories. So we've already seen this sort of structure in the previous example. So a couple other general remarks before moving on. Decomposition is different from spontaneous symmetry breaking, which is certainly on the face of it related. So in spontaneous symmetry breaking, one has superselection sectors, which are separated by dynamical domain walls and are only genuinely disjoint from one another deep in the infrared. So in effect, there's only one overall quantum field theory. If you just go to high enough energies, you can pop from one vacuum over to another vacuum. The idea of a decomposition and the universe of decomposition is that the universes are separated by non-dynamical domain walls that are disjoint at all energy scales. So you really have multiple different quantum field theories present. The principle is that, ideally you shouldn't be able to just go to high energies and fall back into a different vacuum. The idea is that these really should be completely different things, which are simply being superimposed on top of one another, like some sort of moire pattern, to get some naively new theory. All right. So what we've seen is just the Tanizaki-Unzel example is just one example of this phenomenon. What I wanted to walk through next are some more examples in different dimensions to sort of illustrate some of the different ways in which this can arise. So next, let me consider two-dimensional gauge theories rather than four-dimensional gauge theories. But now let me talk about two-dimensional gauge theories in which a subgroup of the gauge group acts trivially. Now, there's a lot to say about this, and I'm sure if you haven't seen this before, there's a bunch of questions running through your mind. So bear with me for a couple of slides while I try to set this up. So I'm going to observe that these, well, first, are different from ordinary gauge theories in which the gauge group doesn't have a subgroup acting trivially. More formally, these have, in modern language, they have what's called a one-form symmetry. And because we're in two dimensions, if they have a one-form symmetry, they decompose, which I'll describe. So let's do an example. let's consider electromagnetism in 2 dimensions, but let's consider a theory of electromagnetism in which all the matter fields have charges that are multiples of k, so that at least formally, a Z mod k subgroup of the U1 gauge group acts trivially on all the matter. Now, maybe the first question to ask is, how in the world is this different from an ordinary theory of electromagnetism? Why can't I just rescale all the charges to be 1? What is the big deal about having a subgroup that acts trivially? Why does that make a difference? So the answer is that perturbatively, these really are the same, but non-perturbatively, that's only one option. Non-perturbatively, there can be a different theory here. So one way to see this is to imagine adding some heavy, minimally charged fields, masses above the cutoff scale. This will certainly distinguish such cases. The presence of such massive fields can be detected in 2 dimensions via the periodicity of the theta angle, which acts like an electric field background. Basically, if you build a capacitor, then make it big enough, the presence of massive fields will cause the vacuum to break down. And that basically that vacuum breakdown determines the periodicity of the theta angle, and it's determined by, in principle, heavier fields that are present in the background. There are other ways to go about this on a compact 2-dimensional spacetime. We need to talk about defining the fields more rigorously as sections of certain bundles, and then the non-minimality gets encoded in which particular bundles you're choosing. But anyway, technically, this really can make a difference. So at least non-perturbatively, there can be a difference between an ordinary U1 gauge theory and this U1 gauge theory with which a subgroup of the U1 gauge group acts trivially. Now, what's this about symmetries? How do we interpret this in terms of higher form symmetries? I claim this theory has a generalized symmetry that interchanges the bundles or instantons of the U1 gauge theory. So for any one U1 bundle or instanton, depending upon what background you're coming from and what seems more familiar to you, you can take any one given background gauge field configuration and basically tensor in a Z mod k bundle for any Z mod k bundle. Since the Z mod k subgroup of the U1 gauge group acts trivially, this is going to make the same contribution to the path integral measure as this did, but the path integral sees this summing over both this bundle and this bundle. So formally, this is changing one bundle to this tensor product of bundles, or very formally at the level of curvatures. You're replacing one curvature with a sum of 2 curvatures. And this expression is a little bit nonsensical because the Z mod k bundle doesn't really have a curvature, but morally, at a cartoon level, we could think about this as in terms of curvatures like so. Now, because that ZK subgroup acts trivially, the action weighting these different contributions is the same. So this is a symmetry of the path integral, except instead of a symmetry involving an action of a group, it's a symmetry involving some sort of action on the bundles the path integral measure is summing over. It's some symmetry amongst the non-perturbative contributions to the path integral. So it's a symmetry, and because the symmetry parameters themselves have gauge transformations, things like associativity only hold up to isomorphism. So for this reason, this is an example of what we call a one-form symmetry, which I'll denote in one of those 2 ways, depending upon the slide, depending upon context. All right, so far, I've argued that a gauge theory with a trivially acting subgroup has a one-form symmetry that interchanges the instanton sectors. So it's an exotic symmetry that just acts on the non-perturbative sectors in the theory. Now, in 2 dimensions, I've made this claim that if a theory has a one-form symmetry, it should decompose. So what's the decomposition in this context? Sure.
You were slightly wrong. Remember that one? Yeah. There was a slide that stated what the symmetry acts on.
Right, hang on a second. I think that's not that one. Probably at the bottom of, like this one?
Is this all intended for just the 2D case? Yes,
Ye-
that's 2 dimensional.
So in principle, there's something similar that should happen in higher dimensions. For what I'm going to use next, I'm only going to apply it in 2 dimensions. But in principle, if I'm in like 4 dimensions, if I have a 4-dimensional gauge theory in which a subgroup of the gauge group acts trivially, then I would also expect a one-form symmetry in that 4-dimensional theory. Now, there won't be a decomposition, but there would be a higher form symmetry.
So like the uniform statement is that when you have a one-form symmetry, it acts on both.
Yes.
That's also
Yeah.
true in 2D.
Yeah. Fair enough. Yeah, fair enough. That's another way of describing this. Yeah. That's a good point. That would be a better way of explaining it for this audience. That if the one form symmetry is acting on Wilson lines, yeah, fine. That's thank you. That's a cleaner way of expressing this for this audience. All right. Let's see. Give me a second though. Right. So we've got a 2-dimensional theory. It's got a one-form symmetry. What's the decomposition? So here's the claim. A 2-dimensional G-gauge theory with a trivially acting, let's say, central subgroup K is equivalent to a disjoint union of order K copies of G mod K gauge theories, each with a possibly different discrete theta angle. So formally, a G-gauge theory with matter invariant under K is equivalent to some superposition or disjoint union of G mod K gauge theories with different theta angles. So these in this context would be called the different universes of decomposition. And yeah. So for example, let's consider SU2 gauge theory. In fact, a stronger statement can be made for pure SU2 gauge theory, but for the moment, let me just consider SU2 gauge theories just in this context. This implication here is that a pure SU2 gauge theory should be equivalent to a sum of 2 SO3 theories with different what are called discrete theta angles. So analogs of discrete theta angles, but coupling to some topological invariant of SO3 bundles. That's Z2 valued, so it's a little bit different from an ordinary theta angle, but plays a similar role. So SU2 is a sum of SO3 plus and SO3 minus. Now, perturbatively, the SU2 and SO3 plus and minus theories are identical. In fact, ordinarily, I think of a 2-dimensional SU2 theory, a 2-dimensional SO3 plus, and a 2-dimensional SO3 minus as just being different variations on the same theme. The Lie algebras are the same, Feynman diagrams are the same, the perturbative physics is the same. But the claim here is that actually, if you superimpose these two, you get this one. So let's see how that works in a little more detail. So formally, the partition function of the disjoint union can be written like this. Here we have a sum over the different universes. They're indexed by, well, irreducible representations of K, which is a level of detail that isn't really so important for the moment, but that's why there's a little hat over this K. Here's formally a path integral for each of these different universes, suppressing the Fourier-Popov ghosts. This is that discrete theta angle, coupling to this topological invariant of the bundle. Now, if I move that sum inside the path integral, so these two expressions are the same, I've just moved that sum into here. Basically, that sum is moved over to here. So that's all I've done. I just moved the sum inside the path integral. On the left, we have a disjoint union, but on the right, up to a numerical factor of 1 over K, this is a projection operator that's projecting onto states of vanishing W2. So schematically, we like to talk about this as some sort of interference effect between the universes. In the title of this talk, I mentioned multiverse interference. This is an example of formally what's meant in this context. Some sort of cancellation between the different instanton sectors of these different quantum field theories. So on the left hand, we have a disjoint union. On the right, we have what is nominally one quantum field theory with a restriction on these different sectors. So schematically, we're combining two theories to form a distinct third. We have two different theories, the SO3 plus and SO3 minus theories, which we combine to form a single SU2 theory. And again, all three of these theories are local quantum field theories. Ordinarily, we think of them as just being ordinary separate quantum field theories all on their own, but it's a neat trick that one of them, the SU2 theory, can be written as a superposition of the other two. So as a consistency check, sort of a more concrete consistency check, let's look at partition function computations in the case of pure gauge theories. So due to old work of McDowell and Rusakov, and I'm sure many others from the lattice community that I'm not giving full credit to, we know how to write down the partition functions of the pure two-dimensional SU2 theory, and for that matter, a pure two-dimensional SO3 theory. The plus really means that there's no discrete theta angle. The only non-trivial case is the minus. So they look sort of, for pure G gauge theories, they all basically have the same form. It's a sum over irreducible representations of a power of the dimension of that representation, the 2 minus 2G power, where G is the genus of the two-dimensional world sheet you're on, or the two-dimensional Riemann surface you're on, weighted by a factor of the exponential of minus the area of that two-dimensional space-time times the second Casimir. So this is just an exercise in group theory. In this case, for the SU2 theory, we sum over all the SU2 representations. For the SO3 theory, we sum over all the SO3 representations. All we need is the analogous expression for the SO3 minus theory that was worked out by Yuji Tachikawa back around 13 years ago and came up with, you won't be too surprised to hear, a very similar looking expression. The only difference is the sum. Here you sum over the SU2 representations that are not SO3 representations. So the result matches expectations. If you take the sum over all the SO3 reps and add to it the sum over SU2 reps that aren't SO3 reps, the result is just a sum over all the SU2 representations. So the partition function of the SU2 theory matches the sum of the partition functions of the SO3 plus and the SO3 minus theories, as expected. Let's see. So another fun check along a more extreme version of this, along the same lines, let's consider two-dimensional pure gauge theories. So here, it's been argued by several, including some people present in the audience here today, that this is the same thing as a disjoint union of what people like Dan Fried would call an invertible field theory. An invertible field theory is a trivial quantum field theory. It's a field theory with one state, the vacuum. It's a classical field theory to all intents and purposes with, for example, some universal counterterms you can add to actually give a partition function that looks different from one. But to all intents and purposes, it's a sigma model on a point, or with target a point. It's something trivial along these lines. So just as a first consistency check, a two-dimensional pure gauge theory also doesn't have any propagating degrees of freedom. So maybe with hindsight, it's not so surprising that a two-dimensional pure gauge theory can be expressed in this fashion. Now, as a first consistency check, going back to those partition functions I had on the last slide, here's the partition function for a pure G gauge theory on a two-dimensional space-time of genus G. It has this form. In this interpretation, this sum here is exactly a sum over the different universes of decomposition. And each of these terms is just the partition function of one of these invertible quantum field theories. It's a pure counterterm theory that looks like, in fact, I can write down the action. If anyone's curious, I can write down what the action for these looks like. It's a pure counterterm theory that looks like a purely classical theory that's the integral over the Riemann surface of the square root of the metric times the log of dimension r times the curvature of the world sheet plus the second Casimir of r times 1. When you integrate that and exponentiate it, you get the dimension of the representation to the power of the Euler characteristic times the exponential of minus the area times the second Casimir. It's if it would be useful for anyone asking me later, I'll write it down. It's not that complicated. Other special cases, two-dimensional pure U1 Maxwell theory. There's another way to think about the decomposition in this context. This disjoint union over irreps is the same as a disjoint union over charges in that two-dimensional pure Maxwell theory. In fact, this is just a limit of the usual story for superselection sectors. So if I have, ordinarily, if I have a theory of electromagnetism, then I have superselection sectors corresponding to total charge sectors. So here, this is more extreme for two reasons. We're in two dimensions, and it's a pure gauge theory. Because we're in two dimensions, a space like slice is one-dimensional. So a charge is the same thing. A point operator is the same thing as a domain wall. It's separating. It's just breaking a spatial slice apart. You can't get from one side to the other without passing through. The other reason this is extreme is because it's a pure theory. Because it's a pure theory, there are no dynamical fields. So any charge you insert, any domain wall you put there is going to be non-dynamical. So if you have different sectors that are separated by non-dynamical domain walls, that's not a superselection sector, that's really a universe. So it's this combination of two effects. We're in two dimensions, and it's a pure theory that results in what used to be, in more general circumstances, superselection sectors actually turning into the stronger notion of universes. Okay, one other note before going on. In these particular examples of decomposition, there's no instanton restriction. So I made a big deal about that at the beginning, but the point I want to make here is that decomposition is a more general notion than just instanton restriction. Instanton restriction certainly pops up in many cases, but not every example will necessarily involve instanton restriction. This is sort of a fun observation about quantum field theories, that sometimes what you thought was just one quantum field theory is really a Moiré pattern of multiple theories superimposed. Sometimes that will result in a decomposition. Sometimes it can do, or sometimes it will result in an instanton restriction. Sometimes it could be other stuff. All right, let me quickly summarize what we've done so far and then talk about some other examples and more examples. So I've talked about a four-dimensional Yang-Mills with a restriction to instantons of degree divisible by K. I've described a local quantum field theory for that and shown how that's, or reviewed how that's equivalent to a disjoint union of ordinary Yang-Mills theories with different theta angles. I've talked about ordinary two-dimensional SU2 theories with center invariant matter and how that's equivalent to a superposition of two different SO3 theories, or more generally G-gauge theories with center invariant matter. And I've talked about how two-dimensional pure gauge theories are equivalent to disjoint unions of invertible field theories. And there are lots of other examples. So next I want to run through a bunch of examples, and then I'm going to get to some more recent developments. So please do. Okay.
So this decomposition,
Uh-huh.
it says that, does it imply that you start off with a forward Yang-Mills theory and you write it in terms of something that's even simple?
Yeah. Yeah.
So do we learn, does that mean that we should be really working with the simpler quantum field theories, and maybe if we could, like if we understand something in that quantum field theory, then we could get something about different quantum field theory.
That's the applications. I mean, I've sort of squeezed the applications out to the very end because most of the applications I have in mind are more mathematical, but that's essentially the gist of the applications.
I mean, but do you learn anything? For instance, if I work with one of these universes, it's a simpler theory. So maybe I can compute amplitudes there. It's a simpler theory. And then once I work out the amplitudes there, then I sum up all these other universes and get the amplitudes for a much more interesting universe. Well, a sum of universes.
No, that's exactly it. So in an example like this, I mean, the computational gain wouldn't seem that big. I mean, four-dimensional Yang-Mills, we've added a couple of extra fields and other local action. Doing a computation over here does not look significantly more painful than computation over here, but in principle, one can do that. But there are circumstances in which there's a significant computational enhancement. So the examples, so bear in mind why I tell you just a little bit about mathematics. I was going to mention this at the end, but since you've asked this particular question, one of the fun applications to this is to, let me back up and give a little context. I grew up doing string compactification, so I tend to think about that part of mathematics a bit. One of the fun applications of string theory to mathematics is something called Gromov-Witten theory, which is basically a theory of counting minimal area surfaces in spaces. We could do the same thing in sigma models. For this talk, I haven't. For this talk, I wasn't really planning to because I figured no one here would care. And I still think probably no one here cares, but bear with me for about 3 minutes while I outline it. We can also do this in sigma models. In sigma models, I can build an example of a sigma model that has a higher form symmetry by considering a sigma model whose target is something called a gerbe, which is some sort of generalization of a space. And for example, if I have an orbifold in which a subset of the gauge group acts trivially, that's basically equivalent to working with a sigma model whose target is a gerbe. Anyway, in terms of Gromov-Witten theory, you can apply this to questions about Gromov-Witten invariance of gerbs. Now, the mathematicians have worked out a theory of Gromov-Witten invariance of gerbs. This is due to Chenruan and Abramovich, Graber, and Vistoli from around 2000, 2001, somewhere in there. So about 25 years ago now. And it's disgusting. It is well and truly just incredibly messy. On the other hand, decomposition predicts that you don't have to work so hard. If a sigma model on a gerb whose target is a gerb is equivalent to a sigma model whose target is a disjoint union of spaces. And something that was proven around 2008 by Zhenhua Zheng and various others is that, in fact, as predicted by decomposition, the Gromov-Witten theory, this complicated Gromov-Witten theory of a gerb, is the same thing as the Gromov-Witten theory of a disjoint union of spaces, which is comparatively much, much easier. So this is an example of exactly what you were suggesting, that if you can, there's really some genuine computational gain. The Gromov-Witten invariance for ordinary spaces, well, they're not easy, but if you're a mathematician who specializes in this stuff, it's your bread and butter, and it's a lot easier than Gromov-Witten invariance of gerbs. But the results, once you know it's a disjoint union, once you work out which disjoint union it is, right, you can just clean that up. And there are some other, examples along the same lines, but I don't want to bore everyone. Suffice to say, you're thinking along exactly the right lines. That's definitely an application of this. Let's see, other examples. So orbifolds. If anyone's really curious, stick around after I'm done with the talk and I will tell you everything you never wanted to know about how to do this same structure in orbifold. So it's not just ordinary gauge theories, it's also finite gauge theories where one can play these games. I've listed here some of the things we've already talked about. So two-dimensional U1 gauge theories with non-minimal charges versus a sum of U1 theories with minimal charges, like the charge P-Schwinger model. Two-dimensional gauge theories with center invariant matter, I've discussed as being equivalent to a sum of G-mod center gauge theories. Pure Yang-Mills theories I've discussed. Two-dimensional non-invertible orbifolds I haven't discussed. Recently, there's been a lot of interest in the community in non-invertible symmetries, which is another way to generalize symmetries. You can define gauge theories in which you gauge a non-invertible symmetry, and you're probably wondering, what does it even mean to gauge a non? There's a bunch of questions you can ask, which I'm not going to have the time to try to get into, but we can also see decomposition in such more exotic cases. There are higher dimensional examples. We talked about one of them. Let me mention in passing a couple of others. We could talk about three-dimensional Chern-Simons theories with a gauged, non-effectively acting one-form symmetry. That turns out to be the same as a disjoint union of ordinary Chern-Simons theory, same sort of game. And then on the boundary, that also works. On the boundary, the first theory has a gauged WW model in which you've gauged a non-effectively acting subset. On the other side, you have each of the boundaries is a effectively acting gauged WW model. Let's see. We could talk about three-dimensional orbifolds by finite non-effectively acting two groups. So it's a higher dimensional, higher form analog of ordinary orbifolds. Four-dimensional Yang-Mills with restriction to instantons of degree divisible by K, I've discussed. There are examples in topological field theory. So I'm not going to spend any time on this, but just for completeness, let me mention two-dimensional unitary TFTs with semi-simple local operator algebras decomposed to invertibles, just like pure gauge theories. And there are some versions of this which don't require so many buzzwords, like a two-dimensional abelian BF theory or the 2D G model, all decompose sort of trivially following exactly that pattern. Sigma models, I mentioned something about sigma models a few minutes ago. This is another thing I'm not going to try to talk about today because I don't think it's really going to be of interest to you all, but it's a thing. And then there are consistency checks. So I don't want to spend a huge amount of time on this. I figured working through examples is more fun, but let me at least have one slide listing some of these. I grew up working with two-dimensional gauge linear sigma models. One can apply mirror symmetry, one can compute quantum cohomology rings, and that all works. In orbifolds, one can compute partition functions, massless spectra, elliptic genera. Actually, in toroidal orbifolds, you can compute everything, and it all works. In open strings, we can talk about boundaries and how to interpret in terms of K-theory. And again, there's some nice story there. We could talk about supersymmetric gauge theories. You could, for supersymmetric gauge theories on spheres, there are exact expressions for partition functions that have been computed using what's called supersymmetric localization. This whole story works out fine there. That's
2D or 4D?
so here the computations have been done in 2D. You can apply, now that you mentioned, there does exist supersymmetric localization computations in 4D. In fact, the original computations were for Wilson lines in 4D. I've never actually done I've never actually checked decomposition. You know, a game I should play. I know, I should give this to a grad student. Take the Tanizaki Unzo example at the beginning, supersymmetrize it, check everything. Apply supersymmetric localization to compute Wilson lines on around the equator of a 4-sphere. Yeah, I thank you for asking that. I think there's a good problem for a grad student buried in there. Let's see, non-supersymmetric pure Yang-Mills. I think we've talked about these two. Adjoint QCD, Zohar had a paper thinking about aspects of that. The Lattice crowd has done some numerical tests of this. Yeah, I've outlined some of these examples. There's also a way to understand this in terms of SymTFTs, which is some newer, more exotic way of thinking about symmetries. Something else I'm not going to spend any time today talking about, but it's a thing if you're curious. Let me go on and talk about the two-dimensional supersymmetric CPN model a little bit to give some flavor of what mirrors look like. And then I want to turn to real gauge theories, and that will probably take up the rest of my time, I suspect. Or actually, speaking of time, I've been talking for about an hour, and I know the talk's listed as going to 2, but I'm not quite certain how that division works. So, okay, so I've covered a bunch of stuff. This seems like it might be a good place to pause and ask your questions. If people want to see more, I can keep on going. I mean, the next bunch of stuff involves relating two-dimensional gauge theories with gauge group the real numbers to two-dimensional U1 gauge theories. So that's a thing. If you're curious, ask me during the question period, which might as well start now.
Any question?
Okay, so probably this was discussed before, but I can ask this question. So given this discussion about the dimensional form of theory and just one and possibly of decomposition, could it be possible that some primary data is related to the continuous in the dimensional form of theory is actually can have some discrete possibility?
So ask the question again.
Yeah.
So ask me the question again. I didn't quite get it the first time, but
So let's think about 4D Young theory.
Okay.
And then you're saying like that theory, because of freeform global symmetry, that is understood as a disjoint union of the theories that takes a theta angle, specifically theta angle. But then could it be possible that theta angle actually that we have in 4-dimensional electricity that is actually able to take some discretizely, not continuous?
Or
like we believe theta can take any kind of
yes,
right? But
yes.
According to like in line.
The decomposition. What the decomposition is doing. So in that case, the Tanizaki Unzo example. If I might be misunderstanding your question, so but feel free to correct me. I described it with a vanishing theta angle, but we could just as well add an arbitrary theta angle in, and then the whole story would run exactly the same. The only difference is that each of the different universes would now have the original theta plus 2 pi m over k. You just add that kth root of unity to whatever theta angle you started with. So you can repeat the story for an arbitrary theta angle, and it will go through in exactly the same way. Each of the universes will then have, instead of a theta angle equal to 2 pi m over k, it'll be shifted by some amount theta, the same shift for all of them. I don't know if that's exactly what the question you're asking,
it's
but
it's because the relation you're using, you're writing one, right? One is a sum of a whole bunch of.
Yeah,
Right.
okay.
So I think
Yeah.
Gomjong's question is asking, well, what if I had a continuous parameter? Can I write that as a sum?
Okay.
And that's
Okay.
not possible.
Okay. Well,
what you're saying is if you have 1 plus theta, well then of course I can just add theta all those terms.
That's right. That's right. And there's just an overall
theta
factor.
overhead,
Yeah. So there.
But
in
that's the
orbifold,
mathematical relation that you were using to
That's right.
arise, right?
that's right. So in the case of orbifolds, we can even see that completely explicitly because in orbifold partition functions, we have, we can write down all the details. Yeah, that's certainly a thing. Now that said, for continuous cases, we think something similar. If you've got 5 minutes, let me jump ahead to the real gauge theory slides because what I'm going to talk about next is very new, and we're still exploring what this all means. But here's what we think is going on. Let me talk about two-dimensional U1 versus real gauge theories, where it looks like there's a continuous decomposition, and then some questions like this are going to become very, very interesting. So let's take up ordinary U1 gauge theory in 2 dimensions with matter fields of whatever charges. Let's replace the U1 by the reals, by that non-compact group, acting on a matter field of charge Q, just like the U1 would, except that now there's some 2 pi times z's worth of trivially acting subgroup. So for real gauge theories, there's other technical questions. One of them is if I want to write down the partition function, it's a non-compact theory. Usually we divide by the size of the gauge group. Dividing by infinity is going to give a 0. There's some questions like that, for which I don't have a genuinely good answer. There are also questions if I have a difference, if I have a non-abelian non-compact group, then the kinetic terms in the path integral measure aren't going to be positive definite anymore. And probably the best way to handle that, Wooden had a paper back around 15 years ago, where he argued that at least in Chern-Simons theory, you could deal with that by analytically continuing in the field space. But I'm not going to go there. All I'm going to talk about is real gauge theories. From the yoga described earlier, if I replace the gauge group, the U1 gauge group by a real gauge group, there's a trivially acting Z subset of the gauge group. I expect a decomposition into universes indexed by rep Z, which is now continuous, which is now a circle, which is going to be interesting for all the reasons just discussed. Each universe one expects should be an R mod Z gauge theory. So what we think is going on, and again, this is a relatively new result. It was just a few months old, and we're still trying to understand all the ramifications. But what we believe is going on is that the real gauge theory, in this case, is equivalent to a disjoint union of a circle's many U1 gauge theories, where the points on the circle correspond to values of the theta angle. Now, let me draw a picture to try to illustrate how this is hanging together. So I don't really have the time to go into this in too much detail, but the theta angles act like -1 form symmetries. They're quantum symmetries that are dual to the global D-1 form symmetry responsible for the decomposition. In principle, in such circumstances, you can go back and forth by gauging. If I start with the decomposing theory and gauge the D-1 form symmetry, I get one of the universes. That universe now has a quantum symmetry, which is a -1 form symmetry. If I gauge -1 form symmetry, that recapitulates the decomposition and generates this. Now there's an issue, because this is continuous, the quantum symmetry, the right way to gauge the quantum symmetry is to do something called a topological gauging. So we're not promoting the theta angle to an axion, we're doing something a little bit different. But we believe there's a circle ideas along these lines. And then we can do various checks. For example, if we look at the partition functions, the way the topological gauging works is basically just to integrate over the theta angles. It's as if we promote the theta angle to an axion and then suppress all the meaningful fluctuations. So all we have left is an integral over theta angles, or integral over the 0 modes. So if we apply that, take this U1 gauge theory, integrate over all of the theta angles, then the result, of course, projects out all of the instantons, which is consistent with the fact that in a real gauge theory, there are no instantons. There are questions about anomalies. If we have let's take the two-dimensional supersymmetric CPN model. I don't have the time. If you're curious, ask me later. I'll walk through that. In terms of pure gauge theories, we believe the two-dimensional pure real Maxwell theory decomposes into a real line's worth of invertible field theories. This also seems consistent with partition functions. The partition function of the real gauge theory by this logic should be an integral over theta angles of the partition functions of each of the U1 theories for any fixed theta angle. The partition function of a U1 Maxwell theory in 2 dimensions with theta angle theta looks like this. Now, the theta angles and these universes connect in a way. If I rotate the theta angle by 2 pi, the universe number increases by 1. There's a sort of a Witten effect for dions that's at work in the background here. So this integral and this sum aren't disjoint from one another. They combine to form an integral over the real numbers. And this Gaussian was, if one believes the results of claims of this paper, that's exactly the partition function of a real gauge theory on a Riemann surface of area A. Anyway, sorry, this was a somewhat long expression about continuous versions of this. And I should add, we're understanding continuous versions of decomposition is still something we are very interested in at the moment, and hoping to get a paper finished sometime.
Don't have any
Not really in 4D. There's the sort of boring thing. I mean, this sort of argument, this sort of topological gauging of the theta angle you could do in 4D as well. It does result in removing all the instantons, just for the dumb reason that if you integrate the theta angles, that's going to project out the instantons. But I don't have an interpretation of it in terms of, it's not a 4-dimensional real gauge theory. I don't know what it is. It's some other thing. But it was, I mean, this 2-dimensional example, in fairness, this actually did appear, or at least a piece of this computation, years ago, back around 20 years ago. Bankstein and Seiberg had a paper where they were attempting to solve the strong CP problem. And they came up with this as sort of their toy model. They didn't phrase it in this language. They weren't doing exactly this. They talked about, they had the idea of, okay, promote the theta angle to an axion, but then let's do something, I forget what they said, to freeze out all the fluctuations. And so they basically just wanted to integrate over the zero modes, which is exactly what's going on there. So in fairness to others, the idea of thinking of this as a toy model to attack the strong CP problem, that's definitely in the literature, but I don't have, and I'm certainly open to discussing it. I don't have anything to say about it myself, though. Other questions?
One more question.
Go for it.
What about applications to gravity, or is that just premature, like gravitation sometimes to play this game, or is the idea of high-form symmetries not well established?
I kind of want to say yes. The basic, I haven't seriously investigated gravity. The good reason I haven't seriously investigated gravity is because of the lore running around many parts of the field that theories of gravity, a quantum theory of gravity, should not admit any global symmetries. So, now that said, I'm sure there are lots of workarounds and, next door neighbor sorts of arrangements one could do, but I've, given only finitely many hours in the day, I've sort of set aside questions about gravity or.
Gravity. Well,
Disjoint from this.
Yeah, no,
Well,
it's definitely
you never know.
disjoint from this, but it's just wondering
Whether there's some
there's
connection.
nothing.
Yeah, I mean, the honest answer is I don't know. I'd be very curious, but I've veered away from questions about gravity. I'm sure that there is some. I feel certain that there are some good questions that could be addressed, even working around the yoga that global symmetries don't exist in quantum theories of gravity. But given up.
But don't just do a frequency for the gravity, like which is for example like just the shift of the 3 gravity from free form, whose D is equal to R and G, right? So then like shift of is preformed by the closed preformed parameter is, I think that's a preformed symmetry in order gravity. Like forget about the quantum gravity or and you still think about the frequency symmetry, which is again the shift of the gravitational free form whose flux is on the two. Then I think that you have a free form symmetry there for the gravity.
But it's probably by the quantum gravity. I guess that's
definitely the yoga people have been using, but I don't know. I don't
Is that
know.
really a symmetry of that?
You shift by free form, close to free form.
No, but the
And I don't doesn't
there's sorry.
the three
Now
the flux is already
the Ritchie scalar term. I don't think that is. There's no such thing.
why would you still transform this? I am talking about the shift of the free form whose flux is already.
There's no. There's no. I don't think there's no such. I mean, you're talking about some particular shift of the gravitational or the metric. And I think that the thing
Okay, there was corresponding shift of the
and I think that whatever that is, in this case, will not be right. I don't think that there's supposed to be a symmetry. Even Einstein said it should not be.
Okay.
I mean, if there were, there'd be serious problems with black hole physics.
All right. Sounds like you guys have answered the question, so I will.
For speaker again today we are going to look at the out of dimension flow.
See, I assume it's okay if I leave the Zoom?
Yeah. Yeah. I'm so sorry I forgot to tell you this seminar is 1 hour long.
Oh, it's all good. Well, but actually, I think there was a pretty natural stopping point. You know, I listened to a bunch of examples. That was a good place to have a conclusion. So I think in terms of timing, it actually worked out just about right.